Hello everyone, my name is Axel Aguerreberry, and in this opportunity I will present the work that was my final thesis project for obtaining my bachelor's degree. The name of the work is Segmentation-free estimation of aortic diameters from MRI using deep learning. The determination of maximum aortic diameters using different images techniques is crucial for detecting different cardiovascular diseases such as aortic dissection, aortic hematoma, and aortic aneurysm. The diagnosis and monitoring of these diseases require precise and reproducible measurements of the aortic diameters for optimal treatment decision-making. Currently, these measurements are done manually by physicians, being time-demanding and suffer from observers' variability and from poor reproducibility. The inter-observer measurement variability of proximal aortic diameters ranges between 1.5 and 1.6 and 5 millimeters. Traditional approaches for automatically estimating the aortic diameters require, as the first step, the segmentation of the vessel. Segmentation is typically performed following supervised learning approaches, which require full expert delineation of the aorta. The process is not only time-demanding, but also observer bias. As a consequence, the segmentation performance affects the diameters measurement. Different segmentation techniques have been proposed to estimate the cardiac parameters. In this work, we propose an end-to-end framework for automatically regressing the aortic diameters from MRI angiography data. Our approach receives as input the 3D angiography scans and outputs the measured aortic diameter at a specific location. No aortic mask is required as input. Our dataset consists of 100 cases. The sequence employed was a free-breathing ECG trigger steady-state free precession. The studies have been acquired with a 1.5 Tesla scanner at Dijon Hospital, France. The resolution between cases varies by some millimeters. We follow the conventional clinical process to evaluate and diagnose the aorta. The database annotations have been performed by several different physicians of the hospital, where each scan has been annotated by a single time by one of the experts. For each scan, 6 aortic diameters typically used in clinical practice have been measured. Those are the Valsalva sinuses, the sinotubular junction, the ascending aorta, the horizontal aorta, the aortic isthmus, and the thoracic aorta. Our database included not only normal cases, but also different pathological cases, such as cases with aortic dissection and presence of prosthesis. Moreover, with the aim of assessing the inter-observer variability, for each aortic diameter, a randomly chosen 20% of the database has been re-annotated by an expert in the field. All images undergo a reslicing and a fine registration step for homogenizing the scans resolution and for aligning and orienting all scans respectively. After image registration, with the aim of reducing GPU memory, we automatically select 16 central slices of each of the scan that include the whole aorta anatomy. After that, the images are normalized following a CT-score normalization. In the following figure, we can see an overview of the proposed CNN architecture. The network takes as input the sequence of 16 MRI and outputs the corresponding aortic diameter at a given landmark. The architecture consists of 3D operations followed by 2D convolution operations with fully connected layers at the end. The last neuron represents the aortic diameter, and we use leaky relay activation functions for the convolutional layers and linear functions for the fully connected layers. We also use batch normalization and dropout. The proposed architecture was trained minimizing the mean square error with Adam optimizer and mini batch size of 8. We use L2 regularizer, and we train our models for 50 epochs using rotation and Gaussian noise as the data augmentation techniques. We propose 2 baseline models for comparing our method, a 3D regression CNN and a 3D multi-resolution 3NN. The 3D regression model is a 3D fully version of the 3D plus 2D model we saw before. All convolutions here are 3D. we try to keep the network as close as possible to our proposal. That's why the amount of parameters of this model was kept similar to the 3D plus 2D CNN. Activation functions are liquid relu. The 3D multi-resolution CNN was implemented and trained. We implemented and trained a model that was originally devised for predicting disability outcome in patients with multiple sclerosis. We adapt the architecture for addressing our problem, and our adaptive implementation consists of 3 consecutive 3D convolutional blocks, followed by a fully connected layer. In this work, we assume that the same model and training strategy could be shared across the 6 different Aortic diameters. That's why for selecting the optimal model and for conducting e-parameter tuning, we first experiment taking into account the annotation of the Valsalva sinuses, since it's generally a challenging measurement, and then we replicate for the other landmarks. In the following table, we can see the effect of the registration approach. We compare 3 different preprocessing pipelines using affine registration, rigid registration, and no registration. We can see in the table that there are some advantages using affine registration in the pipeline, since it's achieved the lowest error and the highest Pearson correlation coefficient. Regarding the effect of the chosen architecture, the CNN made up of 3D plus 2D convolutional layer was consistently better than the other models by reaching the lowest mean absolute and mean square error and the highest Pearson correlation coefficient. These results show that incorporating 2D convolutional after the 3D layers improves the overall performance. The following table summarizes the inter-observer errors and the performance obtained by the model at its Aortic locations. We can see that the prediction errors for each landmark are very similar, with tiny difference that can be attributed to the complexity of the Aortic anatomy. Overall, our model achieved a mean absolute error between 2.2 and 2.4 millimeters, which is less than 1 millimeter of difference of mean absolute error compared against the experts, which obtain a mean absolute error between 1.3 and 1.7 millimeters. The Blunt-Altman plots at each of the 6 locations show a low mean bias at all locations without a clear trend towards under or overestimation of the diameters. As conclusion, in this work, we propose an end-to-end segmentation-free 3D plus 2D CNN for the direct estimation of aortic diameters. The method outperforms a 3D CNN and a multi-resolution 3D in terms of mean absolute and mean square error and Pearson correlation coefficient. The proposed model achieved performance almost at the inter-observer variability error, which is less than 1 compared to the expert's variability. This work allows to continue researching intelligent algorithms devised to directly estimating anatomical structures without image delineation. There are much considerations towards its translation to clinical settings. We aim to improve the model performance by making use of problem-specific data augmentation, and we also aim to allow anatomical localization into the convolutional network. Another approach could be to compare our method with a landmark detection model. Finally, another future perspective is exploring multitask learning models for performing multiple aortic location estimations with a single model. Thank you very much.